Unit 9 is all about right triangles. Today we're going to start talking about the Pythagorean Theorem and its converse. The first thing we're going to talk about is a Pythagorean triple. And this is something that definitely comes up on the quiz and the test, so we want to make sure that we are remembering what a Pythagorean triple is. A Pythagorean triple follows two requirements. The first requirement is that it is a non-zero whole number. And then the second requirement is that it satisfies the equation a squared plus b squared equals c squared. Some examples of Pythagorean triples that are common are 3, 4, 5, 5, 12, 13, 8, 15, 17, and 7, 24, 25. Because we're focusing so heavily on right triangles this unit, I did want to point out some right triangle vocab. The number one thing that we're going to see when we talk about right triangles is the hypotenuse of our right triangle, which is always directly across from the right angle. And then the other two sides we call the legs. So the first theorem that we're going to talk about here is the Pythagorean theorem, and we've seen this multiple times before. This first theorem is your standard old Pythagorean theorem. This is used to find missing legs or missing side lengths of right triangles. And it says we can take the two legs and the hypotenuse of our triangle and set them up in this formula, a squared plus b squared equals c squared, where c is the hypotenuse of that triangle. Again, this only works in right triangles, so we have to have a right triangle first before we can use the Pythagorean theorem. Then we talk about the converse. Now, the converse of the Pythagorean theorem essentially is saying the same thing, but converse means we're going to say that thing backwards. So it says, if my triangle satisfies the equation a squared plus b squared equals c squared, so that must be true first, then it is a right triangle. So this is used to prove triangles are right. You're going to set up your three values into the Pythagorean theorem like you can see here we've done in this example, and you'll either get something that is equal, like in this example, 7,225 is equal to 7,225, in which case you have a right triangle, or you can get something that is not equal, in which case we call those triangles non-right. In the case that our triangle is non-right, we have two different options. So that's where theorem 8.3 and 8.4 come in. The two options that we have for non-right triangles. So we're still using that same Pythagorean theorem. I'm going to refer to it as the hypotenuse, but technically because we don't have right triangles, we can't really call that a hypotenuse. But for our purposes, we're going to call that longest side of our triangle still the hypotenuse. If that hypotenuse is larger than leg 1 squared plus leg 2 squared, then our triangle must be an obtuse triangle, which means that we have one angle that is greater than 90 degrees. On the opposite of that, if our so-called hypotenuse, aka the longest leg, is less than leg 1 squared plus leg 2 squared, then our triangle is acute, which means all of the angles are less than 90 degrees. So again, to recap, if the hypotenuse is larger than the sides, it's obtuse. If the hypotenuse is smaller than the sides, it's acute. And if the hypotenuse is equal to leg 1 plus leg 2, then we have a right triangle. So let's get into the examples. So the first example says, do the lengths of the sides form a Pythagorean triple? The first requirement to be a Pythagorean triple is that we have non-zero whole numbers. And the second requirement to be a Pythagorean triple is that it satisfies the Pythagorean theorem equation, a squared plus b squared equals c squared. So we're going to check both of those things. In letter A, the numbers 5, 12, and 13 are all whole numbers and they're all non-zero, so that first requirement is met. And then we're going to go ahead and put those three numbers into our Pythagorean theorem, 13 being our hypotenuse. So 5 squared plus 12 squared equals 13 squared. And we're going to end up with 25 plus 144 equals 169, aka 169 equals 169. Because we have a true statement here, 169 equals 169, we can say yes, definitively, this is a set of Pythagorean triple. Same thing in letter B. The first thing we're going to check is if we have whole non-zero numbers, which yes, we do. And then we're going to check those in the Pythagorean theorem. 6 squared plus 10 squared equals 20 squared. This is 36 plus 100 equals 400. And we know that 136 is not equal to 400. So this would not be an example of a right triangle. Of a Pythagorean triple or a right triangle. And then lastly, letter C, we do our first check, non-zero whole numbers, and we can see the square root of 13 is not a whole number, so it fails that first check. Therefore, we do not have a Pythagorean triple here. Moving on to the next example, this is probably what we know the Pythagorean theorem for the most, is when we use it to find a missing side. So I'll set up my equation here, x squared plus 10 squared equals 25 squared, or x squared plus 100 equals 625. X squared equals 525. Square root both sides. X equals, let's break this down into 25 times 21, aka 5 radical 21. Same thing here in letter B, we're going to take our legs, the square root of 2 squared plus 4 radical 3 squared equals our hypotenuse, x squared. If I multiply a radical to itself, or if I'm squaring a square root, that square root cancels itself out, so that's 2. 4 radical 3 we want to be careful with. We are squaring 4 and radical 3 here. That's just a monomial inside those parentheses. So that is the same thing as making sure that we square both pieces. 4 squared is 16. The square root of 3 squared is 3. So this is 2 plus 48 equals x squared. 50 equals x squared. Square root both sides. 25 times 2 gives me 5 radical 2 is my x value. Okay, moving on to letter C. In letter C, we actually have one of these quadrilaterals that we've talked about before. These have 4 congruent sides, making this a rhombus. So that tells me that each one of these sides is 3. Also, a property of a rhombus is that those diagonals that are running through the center of that rhombus are perpendicular, which means I get a right angle and a right triangle. That right triangle, if I were to draw it out over here, would look like, here's my right angle, my hypotenuse is 3, and my legs are 2x and x. Therefore, my Pythagorean theorem should look like x squared plus 2x in parentheses squared equals 3 squared. Now, the reason I'm putting that 2x squared in parentheses is because if we don't put it in parentheses, then 2x squared will look like that. And if I do put it in parentheses, if I remember to put it in parentheses, which I hope you will, 2x quantity squared means I'm squaring not only the x, but also that coefficient, that 2. So 2x quantity squared should be 4x squared. Now I'm going to drop everything else down. X squared plus 4x squared equals 9. We combine these like terms to get 5x squared equals 9 and divide by 5. X squared equals 9 over 5. We're going to square root both sides. Now 9/5 doesn't break down nicely, so we're going to go ahead and separate that into a numerator and a denominator. The square root of 9 is 3 and the square root of 5 doesn't really have anything we can simplify it down to. However, we know that we can't leave our answer like that because we have a radical in the denominator of a fraction. So we're going to have to rationalize that fraction by multiplying by that radical on the top and the bottom, which gives me 3 radical 5 in the top and a 5 in the bottom. Lastly, for letter D, we're doing the same exact thing. We're going to go ahead and start with our Pythagorean theorem, 9 squared plus, in parentheses, x minus 3 squared equals x squared. I'm going to give us another angry face over here to remind us that when we do x minus 3 quantity squared, we cannot change that into x squared plus 9. We have to instead expand that into 2 binomials and FOIL. Now, if I drop everything else down, I have this polynomial. I'm going to continue combining my like terms here to get x squared minus 6x plus 90 equals x squared. When I subtract my x squared from both sides, those cancel out for me. Negative 6x, I'm going to move my 90 to the other side and then divide by negative 6. So x is positive 15. All right, now to finish it off, we're going to talk about those theorems at the end of that page. Number 4 says, if these are side lengths of a triangle, is it a right triangle? Now, we haven't talked about this idea of how to say that 3 lengths can make a triangle in a couple units. But if you recall, that rule is that the smallest 2 sides, so let's call them the small and the medium, have to add together to be greater than the largest side. So we can check that really quickly here. We have 9 plus 36. Is that going to be larger than 39? Yes, it is. So these 3 sides do make a triangle. Now we're going to figure out, do they make a right triangle? And to determine if they make a right triangle, we're going to prove that a squared plus b squared equals c squared. So I know that my longest side needs to be my hypotenuse. So I'm going to use 9 squared plus 36 squared. And I don't know what it is yet. And then 39 squared. 9 squared, 81. 36 squared, 1296. And 39 squared, 1521. These add together to 1377, which is smaller than 1521. Now, clearly 1377 is not equal to 1521, and in order to be a right triangle, we need that equal sign. So these are not a right triangle. In fact, we can also go a little bit further and say that because we know this hypotenuse, not really a hypotenuse, but kind of a hypotenuse, is larger than the 2 sides, we actually know that this is going to be an obtuse triangle. It wasn't asking us that, but we can say that pretty easily. Now let's continue. This is more like what you're going to see on the test or the homework, is where we are given 3 numbers and we have to figure out if they are acute, right, or obtuse. So let's review those rules. If it's acute, my hypotenuse is going to be smaller than the legs. If it's right, it's going to be an equal sign in the middle. And if it's obtuse, my hypotenuse squared is going to be greater than my 2 legs, or the hypotenuse is large. So we're going to set up these equations with just a blank in the middle because I don't know what sign I'm going to put in there. We're going to make sure that we put our hypotenuse in the right spot. The hypotenuse is always the longest side. So this should look like 11 squared plus 12 squared, a blank, and 15 squared. $121 plus 144 is 265, which is greater than 225. 15 was like my so-called hypotenuse. And because that's smaller than 265, we're going to call this acute. We're going to repeat for B. What I always want to look for is what is the longest side so that I know that that's my hypotenuse. And if off the top of your head, like me, you don't know what 2 radical 3 is, just plug that into your calculator. You're going to find out it gets you about 3.4. So then we know that 5 is actually going to be our largest side. So I'm going to do my equation, 2 radical 3 squared in parentheses plus 2.4 squared, a box, and then 5 squared. Now we have to make sure that we put that 2 radical 3 in parentheses because I want to square not only the radical 3, but also the 2. So 2 squared is 4, radical 3 squared is 3, 4 times 3 is 12. 2.4 squared is 5.76. 5 squared is 25. This is 17.76, which is less than 25. That kind of hypotenuse, kind of not hypotenuse, is larger. Therefore, we call this obtuse. And that's all.